Hi pre-calculus friends, we're in section 12.5 and we're going to be talking about sigma notation and the nth term. Let's get down to some vocabulary. So sigma notation, if you know what the Greek letter sigma looks like, and I sadly don't write this as nicely as I'd like, so it should be something like that. This actually means summation, kind of like when we were adding up our series values. So if I were to have, let's say, sigma, let me try again, practice, and you should practice too. If we would have sigma from n equals 1 all the way up to, let's say, 5, n equals 1 to 5. What that means is if I had an expression like, let's say, n, 3n, what this means is that I would take 3 times 1 plus, so that's the first one, 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. That's what this notation means. So the sigma notation means that you're going to be adding up. You're dealing with a series, and that series is defined by an equation here, this, or an expression here, that's 3n, and I'm going to calculate that value from n equals 1 all the way up to 5, or whatever this ending number is. And so what n is referred to is the index of summation. So I'm going to highlight that and say that that's what n is. That's the index of summation. We have sigma notation, and that's what we're writing here. Here's the sigma symbol, and this whole situation would be sigma notation. Well, this really is sigma notation. And then n factorial. Well, I talked about this in the last video because I thought we talked about it before, and if it was the first time I talked about it, I apologize. But n factorial is written like this, and when we deal with it, just go over it real quick. When we deal with any number factorial, we can only deal with non-negative integers. So believe it or not, 0 factorial, and you can, there's a cool YouTube video about this, is equal to 1, and 1 factorial is equal to 1, which is weird, I get it. 2 factorial is equal to 2 times 1. So here's where the pattern really starts to be seen. 3 factorial is equal to 3 times 2 times 1. 4 factorial is equal to 4 times 3 times 2 times 1. So you can kind of get an idea of where this is going. Factorial values can get really big really fast. All right, so let's take a look at this bit of information. So sigma notation is given for the sequence. If you've got a sequence of values, a sub 1 all the way up to a sub whatever, the sum of the first k terms can be written like this. So a sub n, or a sub 1 all the way up to a sub k, can be written like this. And this is usually the descriptor of the terms, or like an expression, okay? So here we have a couple of examples. Let's do A and B. So 1a, it says write the expression in expanded form and then find the sum. So we're going to deal with n squared minus 3. So a sub 1 will be 1 squared minus 3, which is 1 squared minus 3, which is going to give us negative 2. So I'm going to add negative 2 to, I'm just writing it out so you can see where it's coming from. This is going to be 2 squared minus 3, which is 4 minus 3, which is 1. And then a sub 3 is going to be 3 squared minus 3. And then a sub 4 is going to be 4 squared minus 3. You see that? We're just plugging in that subscript number right in for n, and we will do it from the index number 1 all the way up to 4. So if I were to calculate that, I get negative 2 plus 1 plus 9 minus 3 is 6, plus 4 squared, 16 minus 3 is 13. When I add all of this business up, I get 19, 20 minus 2, I get a positive 18. So that is the value of this expression here. Let's go ahead and look at this next one. So if I wanted to calculate this, now this is going all the way up to infinity. So writing it out is not going to be the way to do this problem. So let's go ahead and rewrite it down here so we have a little bit more space. If we think about the first term, a sub 1, we're going to plug a 1 in here, and then we're going to end up with 5, because we're going to have 1 minus 1, which is 0. That to the 0 power will just be 5, and then to that we're going to add the following number. We're going to add 5 negative 10 over 7, because that would be a sub 2, so that would be to the first power, and we'd keep going. Do you guys see how we got that? The next value would really be a positive, let's see, we're going to have 2 times 2, which is going to give us the 49 in the denominator, and then we're going to multiply that 4 times 5, so we're going to get 20 over 49. And then the next value, if we were to calculate, we're basically taking this number and we're multiplying it by negative 2/7. Are you guys with me? So if I multiply this by negative 2/7, I'm going to get a negative 40 over 343. So you can see that this is a geometric series, right? You can see this is a geometric series where the R value is this negative 2 over 7. Now, since this R value is negative 2/7, we can tell that this should have kind of a, we can tell that this series should have a sum. Remember, we can get a value for S if and only if R, the absolute value of R, is less than 1. Well, we have that. So now that means we can employ that formula that we had. Do you remember that formula? It was S, the sum of the series, is equal to a sub 1 over 1 minus R. And so what we'll do is we'll take the first term, a sub 1, which is 5, and subtract underneath it 1 minus a minus 2/7. And from that we get 5 over, what's that, 7 over 7, 9/7, or better written 35/9. So if we were to add all of these up, we would get 35/9. That's where we would, this series would add up to, where it would kind of converge to. In example 2, we're referring to the stuff at the beginning of the chapter information. So we've got manufacturers are required by the EPA to meet certain emission standards. If these standards are not met by a pre-assigned date, the manufacturer is fined. To encourage swift compliance, the fine increases a specific amount each day until manufacturer is able to pass inspection. So suppose a manufacturing plant is charged $2,000 for not meeting its January 1st deadline. The next day it will be charged $2,500, and the following day $3,000, and so on, until it passes inspection on, let's say, January 21st. So we're going to find the total amount of fines owed by the manufacturing plant. So how much is the company fined on the 20th day? So if we think about this, we've got a sub 1 being 2,000, a sub 2 being, so a sub 1 being 2,000, a sub 2 being 2,500, a sub 3 being 3,000. And then what we realize is that we're kind of dealing with an arithmetic sequence where the common difference is 500. So I want to know what's happening on a sub 20, right? Because we're talking about the 20th day. And so we remember that a sub n is equal to a sub 1 plus the quantity of n minus 1 times the common difference. And since we're dealing with the 20th day, we're going to write it like this. A sub 20 is equal to 2,000 plus 19, that's n minus 1 times 500. And so when we put all of that together, we get that on the 20th day, the company or the manufacturer will be fined $11,500. The next part of this, part B, asks what is the total amount of fines owed by the manufacturing plant? So we're to assume that every day the charge is compoundable. So the $2,000 doesn't get replaced by the $2,500. It's $2,000 for that first day, $2,500 for the next day, so forth and so on. So we are looking at the sum of an arithmetic sequence. You remember how we did that? The formula was S sub n is equal to n over 2 times a sub 1 plus a sub n. So remember, this was when we talked about Carl Gauss and how he was left to add up a bunch of numbers, all this stuff. All right, so this is where we get that formula from. So we need to know the first and the last term. So the first amount was $2,000. The last amount by the 20th day was $11,500. And we're going to add that up, and we're going to multiply it by the number of days divided by 2. So that's 10 or 20 over 2, which is 10. So we get that. And when we calculate that total amount owed, we get the whopping amount of $135,000, which is quite a bit. All right, so we get $135,000 is the total number of fines. And then finally, part C, it says represent this sum by using sigma notation. Okay, so how will we do it? So we know that we're going to be dealing with days 1 through day 20. So n equals 1 to 20 is what we're going to be dealing with. And how do we represent n in each of this case, right? So we can say that a sub n is really equal to, well, we know the first one was, let me think about a good way to do this. So we're thinking about what a sub n should be. We're thinking about what a sub n should be. And we know that a sub n is equal to, we had the formula somewhere, let's do it again, is equal to a sub 1 plus n minus 1 times d, the common difference. And so that's what I want here. So I want my 500 here, that's my a sub, no, not 500, my 2000 here, that's my a sub 1 plus n minus 1, I gotta leave that there, and then my 500 here because that's the common difference. And if I were to simplify this, this is true and this is good enough, but if I were to simplify this, I would get, let me see if I can write this nice and neat, guys. Let's see what I can do. N equals 1, 220. Going to distribute that. 500 goes here and 500 goes here. So I end up with 500n, right? And then this is a negative 500 plus 2000 plus 1500. And so this is my way of doing part C. That makes sense, guys? So we see A, B, and C done. Hopefully that makes sense. Let's go ahead and take a look at this. Express the series, this series here, using sigma notation. Well, let's see if we can figure out what's going on. So this isn't particularly straightforward or very easy to see, but if you notice 15, 24, 35, 48, these are all one off from a perfect square. So 16 minus 1 is 15, 25 minus 1 is 24, 36 minus 1, you see where we're going. So if we think about this as perfect squares minus 1, this series starts with 4 square minus 1. Are you with me? So we could write the sigma notation as follows. Let n equal 4, and we can go up to, well, what is this guy? Since it ends here, that's going to be 12 square minus 1. 144 minus 1 is 143. So we're going to go from 4 to 12. Are you with me? And then, so what is it? It's going to be n squared minus 1. Is there another way to do this? Yes. There's another equation that you can come up with. We won't talk about it now, but do know that this is not the only way to do it. I'm sure we could have done it where we started with 1, but this is how, this is probably the most straightforward and easiest way to do that. Let's go ahead and look at example 4. Example 4 is bringing us to the concept of n factorial, which we talked about a couple times already. And so we see a definition of what it is. And so we're going to express this series using sigma notation. And so what I want you to see, a couple things, is that when you have sign changes, like this first term is positive, this one's negative, this one's positive, this one's negative, the way to get that is to take -1 and raise it to a power. If you take -1 and raise it to an even number power, it's going to be positive. If you take -1 and raise it to an odd number power, it's going to be negative. So that's the first thing I want you to observe, that flip-flopping back and forth. So as you know, we're often looking for patterns when we're doing these types of problems, just like we looked for in the last one. And so looking at the sigma notation, we got 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial will be 5 times that, which is 120, 6 factorial would be 6 times that, which brings us to 720, and 7 factorial, well, we see that we have all the digits here, but 7 factorial, just for kicks and giggles, will be 4950. Gets big really fast. Would be 5 1,040. So, you know, we're jumping up. But since if you saw these numbers and you saw these numbers here, you'd be like, oh, okay, I see I've got some factorials going on. So this looks like 2 factorial and 3 factorial, 4 factorial, 5 factorial, 6 factorial. Okay, cool. So we've got the denominator. To get the top, it looks like we got 2, and then this number is plus 2. How can we relate that together? Let's think. If we start off with this as 2, and we see what happened to get from here to here. Well, okay, so I'm thinking it's through. So I put 2, 3, 4, 5, 6, because I'm pretty confident that I want to use 2 factorial down here, 3 factorial, 4 factorial, 5 factorial, 6 factorial. So that means that I'm dealing with a summation notation where n starts at 2 and goes to 6. Are you guys with me? But I have to continue describing everything about this equation as 2, 3, 4, 5, and 6. And I think I got the sign right. If I put -1 to the second power, that's going to be a positive number. So this whole number is going to be positive. And if I put -1 to the third power, that would be the third term, then that's going to be negative. So I'm cool with that. So I'm going to write this part that I have down so far. So I've got n factorial in the denominator and -1 to the n at the top where I'm starting with 2. Now the next question is, how can I get a 2 here and then a 4 here and then a 5 here and then a 6 and then an 8 and then a 10? So I was like, okay, what do I have to do? What can I do to 2 to get 2? What can I do to 3 to get 4? What can I do to 4 to get 6? And what I realized it's going to be 2 times n minus 1. Are you with me? So n minus 1, if n is 2, 2 minus 1 is 2 minus 1 is 1 times 2 is 2. So I have 2 over 2 factorial, or 2 over 2. Then I can do the same thing here. 4 minus 1 is 3 minus 1. It makes sense, I promise. 3 minus 1 is 2. 2 times 2 is 4. 4 minus 1 is 3. Multiply that by 2, you get 6. So this works. Now the reason why I kind of belabored this, I didn't want to use the equation in the text, not because it's bad or wrong or hard. I just wanted to puzzle through it, because I know as good citizens of mathematics, you guys will have to puzzle through this stuff too. So here's one answer to example 4. Another answer that they had in our text, I'll write it down if you don't feel like grabbing your textbook, is that they did the summation from n equals 1, which is totally legit, to 5, and they had -1 to the n plus 1 power times 2 to the n, not 2 to the n, times 2n, all of that over n plus 1 factorial. And this too is a correct answer. So the point of this example is to say, hey, it won't always, first of all, our index number won't always start at 1. We saw that in the last example. And I can find another way to do this as well, where we do start at 1, and it'll be a little bit more of a complicated expression, but I think we can do that. And so we're not always going to start at 1, and there's not always one way to explain or to rewrite something in sigma notation. With that in mind, I look forward to talking to you soon. Let me know if there's any questions or concerns. Take care.